Ever since the discovery of polymers, they have been renowned for their insulating properties and resistance to electrical conductivity, or at least this was the case until the beginning of the 1970s, when the combined efforts of chemists Hideki Shirakawa, Alan MacDiarmid, and physicist Alan Heeger led to the synthesis of the first electrically conductive polymers. In this short video, we'll explore the chemistry behind these conductive polymers and a few of their many applications. Before we look in detail at conductive polymers specifically, it is important to understand the general chemistry of polymers. Polymers are a type of macromolecule which are chain-like and made up of smaller units called monomers that are repeated many times. The repeated units are attached to one another via covalent chemical bonds, and the resulting polymer has properties that vary massively depending on the structure of the monomer, or in some cases monomers, that are used. Some common examples of polymers include polyethylene, used in plastic packaging and bottles, which is made up of ethene monomers, and polyvinyl chloride, or PVC, used widely as a building material, which consists of chemically bonded chlorethene molecules. Polymers can be separated into two categories, depending on the mechanism of their synthesis. The first of these categories is chain polymers, which are synthesized via chain polymerization and are made up of alkene monomers. In chain polymerization, a single monomer is reacted with a compound called an initiator, resulting in a reactive monomer molecule. This monomer could be a free radical, an anion, or a cation. This reactive monomer then reacts with further monomers sequentially, opening up the alkene double bonds to give a long polymer chain, which keeps its reactive end monomer throughout the reaction. The two polymers we've just looked at are examples of chain polymers. The second category is step growth polymers. The mechanism of synthesis for these polymers involves a lot of simultaneous condensation reactions, and the monomers must contain reactive end groups. The conductive polymers we'll be looking at are chain polymers, for reasons that will become apparent shortly. To understand the chemistry behind conductive polymers, we'll first look at polyacetylene, a flat polymer with 120-degree bond angles. Polyacetylene is a polymer that contains two isometric forms, cis and trans, and is usually formed as a black powder or film with both cis and trans isomerism. In 1974, in the lab of Japanese chemist Hideki Shirakawa, it was discovered accidentally by adding too much catalyst that it was possible to synthesize polyacetylene that contained only trans isomerism. This trans polyacetylene was silvery and metallic in appearance and was found to be a semiconducting substance. Soon after this, a method of synthesizing almost purely cis polyacetylene was discovered. Cis polyacetylene had a copper-like appearance and was also a weak semiconductor. The real breakthrough came with the help of chemist Alan MacDiarmid and physicist Alan Heeger, who heard about Shirakawa's discovery and invited him to the University of Pennsylvania in Philadelphia. It was here that they began to modify polyacetylene by oxidation with iodine vapor, and it was found that the oxidized trans polyacetylene's conductivity had increased by a factor of 10 million. Let's take a look at the structure of trans polyacetylene in more detail. The alternating double and single bonds along the polymer chain are the key to its conductive properties. This feature of the polymer is known as conjugation. In a non-conjugated polymer, the electrons are unable to move freely between the atoms in the polymer, as they are localized in bonds or on atoms. However, in a conjugated system, such as polyacetylene, some of the electrons are able to move along the polymer and are delocalized. There are two types of bonding in polyacetylene, sigma bonds and pi bonds. The sigma bonding is a feature of both single and double bonds, but the pi bonding is a feature of only the double bonds and consists of overlapping p orbitals on the carbon atoms, resulting in the slight delocalization of electrons across the bond. By alternating double and single bonds, it is possible to extend this effect along the entire polyacetylene chain, and if the chains are packed efficiently enough, this can result in the delocalization of electrons across polymer chains. Conjugation alone is not enough to make a polymer highly electrically conductive. Hence, the early forms of trans and cis polyacetylene were only weak semiconductors. This is where a technique known as doping comes into play. The electrons cannot move easily in undoped polyacetylene because all of the orbitals involved in the conjugated system are occupied by electrons. By removing or adding electrons via oxidation or reduction, the conductivity of the polymer increases dramatically. There are two types of doping: positive, or p-doping, which involves oxidizing the polymer chain with a halogen, and removing an electron from the conjugated system. The other type of doping is negative, or n-doping, which involves reducing a polymer using an alkaline metal and adding an electron to the conjugated system. A good analogy for doping is a tube of sweets completely full. Now imagine you shake the tube. The sweets won't move. This represents an undoped polymer. But if you remove some of the sweets so that the tube isn't full and shake it, the sweets can move. This is what p-doping does. Removes electrons, allowing easier movement of the remaining ones. Alternatively, you could add more sweets, requiring a larger tube that when shaken allows the sweets to move. This is what n-doping does. Fills higher energy orbitals, creating more space for electrons to move. P-doping was used to modify polyacetylene. The resulting doped polyacetylene is a salt, in which the electrons from a double bond can move throughout the polymer, carrying charge and therefore allowing current to flow. The positive charge on the polymer radical cation is fixed in place by the electrostatic attraction to the ions of the doping agent. However, if a polymer is oxidized heavily, the positive charges can be moved along the polymer chains via a complicated mechanism involving the polymer radical cations condensing into molecules called solitons. I won't go into the details of this mechanism in this video, but there's a link in the description to an article that does explain it. The fact that charges, and therefore ions, can be moved along polymer chains makes them extremely useful for certain applications. In October 2000, Shirakawa, MacDiarmid and Heeger received a Nobel Prize in Chemistry for their work, and since the discovery of conductive polymers, the amount of potential applications they have has grown rapidly. If you've recently used one of the newest smartphones, or watched something on a new TV, the chances are you've been looking directly at conductive polymers. For example, OLED and AMOLED displays are becoming increasingly more popular in electronic devices due to the fact that they are more efficient, provide better image quality, have a simpler design, and are more versatile than their widely used LCD counterpart. OLED stands for Organic Light-Emitting Diode, and they are a type of display made up of pixels that contain an organic layer within them that emits visible light when a voltage is applied. Early OLED pixels in the late 1980s used small molecules in the organic layer, but as research in conductive polymer electroluminescence advanced, the first polymer-based OLED, or PLED, displays began to appear, and they are now the most common type of OLED displays. Typically, derivatives of the conductive polymers, polyphenylene and polyfluorene, are used in the organic layer of OLED pixels. You can see that similar to polyacetylene, polyphenylene and polyfluorene are conjugated, allowing them to be electrically conductive. These polymers are also capable of emitting visible light when an electric field is applied, hence their use in OLED pixels. Other molecules and atoms can be substituted onto the polymer main chains to change the wavelength and therefore the colour of the emitted light, making them ideal for use in displays. Another example, and arguably one of the most basic applications of conductive polymers, is in anti-static coatings that protect sensitive electrical components from static shocks. Because the polymers conduct electricity, the charge from the static shocks can be dispersed by the polymer before any damage is caused. Polyaniline is a conductive polymer used in the manufacture of circuit boards to prevent damage to the circuit components. Similarly, a polymer called P-dot is used to coat photographic films and flat-screen displays to protect from static shocks. However, the use of P-dot in anti-static coatings is only the most basic of its uses. This polymer is currently being researched, along with other conductive polymers, for its ability to interface electronic medical devices with living tissue. Pacemakers, used to treat heart conditions, neurostimulators, which help to treat conditions such as Parkinson's disease, and cochlear implants, which help to restore hearing, are all examples of electronic medical devices. The issue with integrating these devices into living tissue is that the systems deal with electrical signals in different ways. Soft living tissue transfers electrical signals using the movement of relatively large ions, whereas the fixed electrical devices we manufacture use the transfer of much smaller electrons. But as we saw earlier, conductive polymers have the ability to move both electrons and charged ions, making them the perfect solution for meshing the two systems together. This, coupled with the versatility that polymers provide, make them ideal for use in this way, as these conductive polymers can be modified and combined with other monomers to change their properties and help the living tissue accommodate electronic implants. These are only a few of the many current and potential applications of conductive polymers, and as more research is being conducted, they'll continue to become a large part of both new technology and everyday life. All the sources used, as well as some reading on the things I couldn't fit in this video, will be linked in the description below. Thanks for watching.